Welcome to SAT Monsters. So, I got this idea from a student basically going over some SAT reviews. And my goodness, I saw this and was like, dude, this is the thing that they do in SAT. So, you go through a bunch of different problems in an SAT test. You're going to have, well, simple ones, things that you're going to be like, potentially duh. And then you're going to get this guy. Let's take it apart piece by piece. And this is from the pure algebra side of the test because there is separations in the test given. So you're going to have a whole section based on algebra and how to apply your knowledge. If you've seen my past videos, I always refer to algebra as the grammar of the spoken language we use in mathematics, right? The vocabulary is calculus, it's statistics, it's physics, it's trigonometry. It's just words or formula that you're memorizing. But in order to apply that formula correctly, it's all about that algebra, about the grammar. Do you work with the correct grammatical steps? So, this is a part of that algebraic grammatical step space. So, here's how you normally approach these. First, what info do we have? Well, not much. In fact, very little. The first thing we can say is, all right, we got a parabola. Cool. A vocabulary word or formula pops up. Ax squared plus bx plus c. Awesome. Then you've got a vertex. Vertex form. A parentheses x minus h parentheses squared plus k. Potentially, right? We're starting to build and recall information so we can choose the right choices in the right direction to go. And then you say, all right, this is the most ambiguous one. Intercepts at 2 points. There's a particular case that we have to remember about intersects of a parabola. And it has to do with the quadratic formula. So they already gave us the first equation, ax squared plus bx plus c. But recall that if you're trying to find x-intercepts, which is the x-axis crossings or x-axis intersects, we need to look at an equation or a formula, the negative b plus or minus square root of b squared minus 4ac over 2a. It's a mouthful. I know some of you are like, oh no, not that one. Yes, that one indeed. But it's not the whole equation we're interested in. In fact, some parts we kind of already have, and we already understand, and we haven't seen them in this form, but if you remember, any vertex form, or the vertex, x value, or call it the x of the vertex, is going to be equal to the negative b over 2a. That should be somewhat familiar. You've seen it pop up if they ask you for the vertex. You take b, you make it negative, and divide it by 2a. Still referencing basically the a, b, and c from the ax squared quadratic formula. But we don't normally associate that with the actual negative b2a here. Voila, that's the first kind of key that, hey, I can remember two equations much simpler, right? But then there's the question of what's up with the b squared minus 4ac. Well, that part we call the discriminant, for whatever reason. It discriminates against different types of x-intercepts. I'm not sure how to put that into words. It's just a choice of the defined area down here. So, discriminant. If I'm spelling it wrong, I'm a math guy, not an English guy, so my bad. But that discriminant's very telling of a couple of options that we can have with any quadratic equation, and that's important. The first case is that we basically analyze where its location is. The location is inside of a square root. That's important because then anything in a square root, we have certain rules for it. The first rule is we can't have a negative number. -2, -5, -10 basically doesn't work. A square root cannot be a negative inside because the number that we would normally square would always turn positive. Square of -2 is -2 times -2, makes a +4. There's no case scenario where a square root going backwards will take a +4 or take a -4 and go back to two numbers, because two numbers multiplied the same way, or a negative times a negative, even a positive times a positive. Regardless, they both end up being positive, and that's normally the case for a square root. Remember, squares and square roots are opposite of each other, just like division and multiplication and addition and subtraction. So there's a case there to remember. One direction to the other direction. 2 squared is 4, square root of 4 is 2. So this case, if we have a discriminant, when we combine all the numbers together with actual values, and we get a negative value, or basically a negative number inside of that square root, we have no intercepts. One can argue we have imaginary intercepts, but they're not real, so we have no real intercepts. But then there's the other case, square root of 0. And for that fact, it's a plus or minus square root of both, if we really think about the plus or minus in the front. That would mean that if we have a 0 square rooted, that's still 0. And a plus or minus 0 doesn't really make any difference because there is no positive or negative 0, it's just 0. It's non-existent, a value or thing that doesn't exist. So this case scenario, we have one intercept. The case for this visually is that we have an x-axis and our parabola just barely grazes and intersects at a one single point location, normally the vertex. Then we have an actual regular value, right? So we've got two cases here so far, and there's a third case where we have a regular positive number. +4, +9, a mixture of numbers that won't square root nicely, but regardless, are real. And in that case, we would get possible two answers, a positive square root of that number and a negative square root of that number. Two x values, which in that visual representation is basically a parabola directly flowing through our x and coming back up through the x-axis, hitting it twice. And what's the first one? Well, if there's no intercept, it's basically like hovering above it. It never actually touches the x-axis, right? This is where the ambiguity just begins. Understanding that one piece now tells us, okay, we're looking for intersects of x-axis at 2 points, so we're more interested in these options here. We want two options. Therefore, we basically need whatever is inside of here, the b squared minus 4ac, to be greater than 0. That's the first case. Oh, this is a monster, and I may not be able to finish it this time around because I'm between sessions right now, and I have this fresh in my head, and I want to go over it for you guys online. And in about 30 minutes, I'm going to go back to my students. So hopefully I can make it finish here, or I will continue it next time, probably about 2 or 3 hours and finish it off then. So wish me luck. It is a monster of a problem. But this is actually a good representation of literally pure algebra. It's when we're playing with math in a certain way, we're just moving and pushing numbers around, making sure we're following the correct algebraic grammar. And trying to basically complete the main goal of every algebraic problem. That goal is to get to a single variable. Because right now we're dealing with a bunch of variables, but how and what can we do to get it basically pinned down to a single variable if possible? So let's see. Now, the other key we're going to need is, well, we already have some details. So that's the first focus, is greater than 0. The second focus is we want to start with what we can basically start writing. Because we have a vertex, we can use the vertex form. Y equals to a x minus h squared plus k. If you're not familiar with the vertex form, make sure you are, because a vertex form basically gives us the h and the k right in the vertex itself. These numbers are the things we can extract right away and then place them appropriately here. So I'm gonna make more room and write it down here. Y equals to a x minus 8, not h anymore, it's a 9 squared plus or minus 14. Okay, we're so close, but we have this a that's unaccounted for right now. But maybe you're starting to see some relations, some possible connections starting to happen, right? Well, the first thing we can do here, or the only thing we can really do here, is expand it, because we are technically trying to follow the ax squared bx plus c, and the question basically wants us to add these three values together to get one of our possible answers. Now, this question actually would not be solvable if we did not have these options. These options basically reduce a variable for us to get to a single variable. And that's really the trick of this problem, is you can do a bunch of math and stuff, but unless they gave you the options, this would be an unsolvable, untestable case. So we expand what we have. So a x minus 9, x minus 9, minus 14. We do some foiling. That's x squared minus 18x plus 81 with the a in front minus 14 at the end. Then we distribute that a that is indeed our crux for our solution. It's a crux because it's not helping us in any way, shape, or form. Normally, we'd like to get to a single variable situation. As you've seen before, we have the case for an a plus a equals to 4. Algebraically, we know a number repeated twice would be 2. Plus 2 equals 4. So there's only one solution that's possible here. But as soon as we introduce a new variable or a different variable, will our options expand to infinity. We can still use 2 plus 2. We can use 8 minus 4 or plus negative 4 for that matter. Like, our options literally go to infinity, and let's not include decimals because we can essentially expand on this forever. So we're trying to get from this to this. That's normally the step one of every algebraic process, is find a way to get from two variables to one. I have 30 minutes, so it should be good to go. Well, we're not so fortunate in our case right here. We can give ourselves the y equals and see that, all right, well, we don't really have one variable. We have a y, we have an x, we have an a. But we have another hidden equation that we can apply for us to kind of remedy that situation. It starts back up here with the a, the b, and the c. Okay? I'm going to try and color code this as clearly as possible. When we look at ax squared, a is in front of x squared, not x squared. Common misinterpretation when you're looking at it for the first few times when you first learn it. X squared is separate from what's in front of it, which is a, which is whatever is in front. It can be 5, it can be 10, it can be nothing, but nothing means the number 1 or 1 times x squared. So it still would be 1 even if nothing was in front. Here, however, we have a. Cool. That's nice. B, for the same factor here, is whatever is in front of x. Not x included, but whatever is physically in front of it. And for us down here, this is in front of our x, a negative 18a. Finally, c is the constant. Now they've told us that a, b, and c are constants, so we can assume that a would be a constant, and c is everything else that would be said constant. We would then consider all of these to be c. All right, almost there. With that in mind, we can now use this little cheat they gave us. The a plus b plus c is equal to one of these answers. We have an a, we have a b, we have a c, technically, right? Our a is a, our b is negative 18a, and our c is 81a minus 14. But if you're clever, you're going to start seeing something that we're trying to approach to based on what I just moved. We're making our way to a single variable situation. Cool. Now, well, we have an a plus b plus c. Now we plug in set a, b, and c, even though they are other variables, we still plug them in because, again, the case scenario is if we can replace things with something a little bit more convenient, do it. No reason to not. In fact, the strategy for many of these difficult SAT problems and ACT problems is start plugging in stuff. At some point, not stuff into random things, obviously, but when you see a quadratic, start laying out all the quadratic possibilities. Plug in some stuff and see if you find some hints. And as long as you're approaching all math in this manner, going from two variables to one, that will help. At some point, it'll click. Oh, if I do this, I get all single variables. AKA, if I plug in these substitutions for A, B, and C, notice that we're left with only A's. So let's do that. A is A, nothing big there. B is negative 18A. And C is 81A minus 14. Simplify a bit because it looks a little messy. Negative 18 and 81. 7, 80, 73, 63. So positive 63A minus 14. And then A in the front. Oh, we can actually go forward with one more combination. That's 64A. There we go. Okay, so now we simplified their assumption of addition equals to one of these possibilities to a nice formula that we can reuse and test with these possibilities. This is the situation where if they didn't give us options, we would be kind of stuck with infinite possibilities, infinite answers. But because they're giving us possibilities, now we can at least test. And the other case is we need to make sure this stays as a rule. We need to make sure we get a number that makes a positive 0 happen here. Now, we can also simplify this with what we have, plugging in some of our variables from above. Negative 18 a squared minus 4a, and that's just 4a, so whatever. And then 81a minus 14. Get some calculations in order. Let me see if I have that shown here. Let me go ahead and pop it up. My little handy dandy calculator. If I have it. Do I? Yeah, there it is. Right? Yeah, there we go. So take that. 18 squared. This is basically you having a calculator on the test. That's a negative 320, positive 324a squared. Then 4 times 81 with the distribution. Interesting, we got a negative 324 with an a squared because of a times a. And then a 4a times 14, 56, positive 56a, and still greater than 0. So conveniently enough, the big ugly numbers cancel out, and we can now check with a much simpler 56, oops, that's nasty, 56a, whatever we get for a has to be greater than 0. So we test. We have a rule that we have to abide by. This is our 2-point situation, our discriminant to be a set of 2 x-intercepts instead of just 1 or none. We've simplified it down to a crunchable equation. And this is the great thing about algebra is you can move variables around to a certain point where you can actually just use a much easier equation later instead of having to plug in over and over and over to test with the original b squared minus 4ac. Okay, and then we commence with our tests. So if we have a negative 23 equals to 64a minus 14, add 14 to both sides. That'll be 23 and 14. This would be a subtraction case. So that'll be 6, 7, 8, 9. So that's a negative 9 because the 23 is bigger. And then we'll divide 64 from both sides and we have a. There's a possible a. So if we were to test this out and say, hey, is this the answer? Well, does it give us 2 points? Well, we have to apply our rule. Now that we get the a, we test it out with the 56, plug in negative 9 over 64. It's going to be an ugly number, but we're basically trying to see if this is greater than 0. But if you do a quick shorthand, it's a negative number divided by a positive number and a positive number. Well, the whole thing is going to end up being a negative number, but a negative number is not greater than 0. So, no, 23 is not our answer. If we do the same thing with b, it's going to be basically the same idea. We're just going to have another negative number. And that's going to be a negative 5 divided by 64 equals to a. But that negative 5 is going to do the same exact thing that the negative 9 did. Hence, that's also a no. So now we kind of have a very quick finale. When do we get a positive number to come out of this process? For C, well, that's going to be actually 0 over 64 equals to A, or A equals to 0. So 0 greater than 0, question mark? No, right? So C is also not the answer. Process of elimination. And the final test is negative 12 equal to 64a minus 14. Add 14 to both sides. That's going to be a positive 2 equals to 64a. Divide by 64, divide by 64. Hey, we got a positive 32, or 1 over 32, but it's overall positive. So technically, we don't really care about the digit here, more the sign, because that sign is going to tell us the case scenario for the rule. And if we apply the rule here, well, 56, plug in 1 over 32. Is that greater than 0? Well, 56 over 32 would be the simplified fraction. Yes, that is going to be a number that's greater than 0 simply because the 56 is a positive number. And D is your final answer. It's a monster. It's an absolute monster. And I'm putting it under the heart of algebra as far as everything we've done before in previous sessions, because there is a very strong correlation between how we handled an equation full of variables to get to a single solve for x situation, getting x on its own on the side. And we discussed in the previous office hours how we do this all the time. Even when we just have pure letters all over the place, we convert a quadratic equation, do some math magic to it, and we give you something called the quadratic formula in terms of x, or solving for x in terms of b, a, and c. And what we tell you is like, hey, just memorize this. Don't worry about where it came from, which is a good thing, but also kind of like it's not. I wish teachers would explain a bit more on the process, but I think honestly, most teachers don't even know how to get there, how to go from a quadratic equation to the quadratic formula. So they basically go the easier route and just say, hey, just memorize it and move on with your day. Right. But the rules that we applied in the previous Heart of Algebra office hours literally apply directly here, but they apply in a more troubleshooting type way. Not only do we need to remember some of the details about a quadratic equation and some of the subformulas involved, specifically the vertex, we had to remember what the discriminant does for our particular checks. And with those two ideas, we build an equation with the vertex formula and the given vertex. We extract a, b, and c. We apply this little a plus b plus c arbitrary. It's not even, no one does that. No one just adds a, b, and c together. It's not a thing. It's basically there for us to have another equation for us to use. They just decided that was clever. But there's no functional reason behind us adding all the constants together. Not at least in algebra. Maybe something further down in calculus or whatever. For a test. Not even a particular significance on observations. Just to see, oh, is this number bigger than this? You get my point. There's really an arbitrary use of this extra equation, but it does help us try now with this modified version of a plus b plus c combined with our extractions, our ABC simplification, a plus b plus c simplification, and our rule. Using these together, we're able to identify negative 12, and notice they say could be an answer. Could be the value. It could be, for sure. It could be because they give us options to try out. But if we didn't have options, it could also be a million other numbers. It'll be basically any number bigger than 12. In fact, negative 13 would have worked as well. Yeah, negative 13 would have worked as well because that would have been a plus 13 on both sides. And a plus 13 and a minus 12 is going to give you a positive 1. So instead of 1 over 32, we would have got a 1 over 64. So really, a negative 13 would have worked too, but it's not a part of our selective options. Right. So negative 11 would work, 0 would work, 1, 2, 3 to infinity would work. So technically, because that's really the first answer that gives us a positive for A, it became the actual answer for the overall problem. But because of the options, that's the only way or only reason we can stop and say there's an actual feasible answer, because they present it as a possibility. SATs. I had this with a student. I had to go over it maybe 2 or 3 times to kind of get the idea for him, but he got it. And it just takes a little bit of, I guess, creativity, because you're using tools that you remember as a flashcard memory, but you're applying algebra to those little pieces of memory to try and figure out, well, what's the best feasible way? Again, we can go from this case scenario, a 2-variable situation, to solve for a single variable, because we can only solve for a single variable. If we have 2 variables, we should have 2 equations, sure. Then it's solvable. Then you can solve. But if you only have 1 equation with 2 variables, it's unsolvable because your options are infinite. You can combine numbers in many different ways to get that answer. So there it is. I just wanted to really go over that in detail. I hope that helped. If you have any questions, leave them in the comments. Like and subscribe for more random stuff that I'm finding with my students. I'm here to patch up any misconceptions or any unclarities in algebra, especially, but I'm here to help out. I do a lot of programming on this channel. I do a lot of mathematics. I play games. I try to entertain and teach at the same time. So if you find this entertaining, well, it's math. So if you find this informative, like and subscribe and put the notification on so we can talk later. And also feel free to message me on chat and stream. Feel comfortable to chat with me, to leave comments. I will reply 100%. I may be a little delayed because as I'm doing this kind of stuff, I'm not really too involved with the chat until I look to the side and be like, oh, somebody messaged me like 10 minutes ago. Please be there. Please be there. I'm about to answer. Um, but I multitasking. Once I get hyper focused on something, it takes me a bit to break out. So thanks for joining. This is the professor, and these are the office hours. And look forward for more of these. So put on your notifications, and